Secure Cloud Network Architecture. Lesson Introduction. Cloud network architecture encompasses a range of concepts and technologies designed to ensure the confidentiality, integrity, and availability of data and applications within cloud-based environments. Cloud architecture and modern software deployment practices enable seamless integration, management, and optimization of resources within cloud-based environments. Key features include on-demand provisioning, elasticity, and scalability, which allow rapid deployment and dynamic adjustments to computing, storage, and network resources as required. Additionally, multi-tenancy and virtualization technologies enable efficient resource sharing and isolation among diverse users and workloads. Cloud architecture also employs load balancing and auto-scaling to distribute workloads evenly and maintain high availability and performance. Furthermore, hybrid and multi-cloud strategies allow organizations to leverage various cloud service providers, reducing vendor lock-in and promoting a more resilient and cost-effective infrastructure. Lesson objectives. In this lesson, you will do the following. Summarize secure cloud and virtualization services. Apply cloud security solutions. Summarize infrastructure as code concepts. Exam objectives covered. 3.1 Compare and contrast security implications of different architecture models. 3.2 Given a scenario, apply security principles to secure enterprise infrastructure. Understanding cloud platform concepts is crucial for security professionals to effectively protect digital assets, ensure compliance, and manage risk in modern IT environments. As organizations increasingly adopt cloud services, security professionals must be adept at identifying potential vulnerabilities, implementing robust security measures, and monitoring cloud-based resources to mitigate potential threats. Familiarity with cloud platform concepts enables security professionals to navigate the shared responsibility model, where cloud service providers and users collaborate to maintain a secure infrastructure. Additionally, understanding cloud technologies is essential for developing tailored security strategies, embracing best practices, and adhering to regulatory requirements. As cloud computing continues to evolve rapidly, security professionals must stay up to date with the latest advancements and threat landscapes to safeguard their organization's valuable data and resources. Cloud deployment models. A cloud deployment model classifies how the service is owned and provisioned. It is important to recognize that deployment models have different impacts on threats and vulnerabilities. Cloud deployment models can be broadly categorized as follows. Public or multi-tenant is a service offered over the internet by cloud service providers, CSPs, to cloud consumers. With this model, businesses can offer subscriptions or pay-as-you-go financing, while at the same time providing lower-tier services free of charge. As a shared resource, there are risks regarding performance and security. Multi-cloud architectures are where an organization uses services from multiple CSPs. Hosted private is hosted by a third party for the exclusive use of the organization. This is more secure and can guarantee better performance, but is correspondingly more expensive. Private, cloud infrastructure that is completely private to and owned by the organization. In this case, there is likely to be one business unit dedicated to managing the cloud while other business units make use of it. With private cloud computing, organizations exercise greater control over the privacy and security of their services. This type of delivery method is geared more toward banking and governmental services that require strict access control in their operations. A private cloud could be on-premises or off-site relative to the other business units. An on-site link can obviously deliver better performance and is less likely to be subject to outages, loss of an internet link, for instance. On the other hand, a dedicated off-site facility may provide better shared access for multiple users in different locations. Community is where several organizations share the costs of either a hosted private or fully private cloud. This is usually done in order to pool resources for a common concern, like standardization and security policies. There will also be cloud computing solutions that implement a hybrid public/private/community slash hosted/on-site/offsite solution. For example, a travel organization may run a sales website for most of the year using a private cloud, but break out the website to a public cloud when much higher utilization is forecast. Flexibility is a key advantage of cloud computing, but the implications for data risk must be well understood when moving data between private and public storage environments. Security considerations. Different cloud architecture models have varying security implications to consider when deciding which one to use. Single-tenant architecture provides dedicated infrastructure to a single customer, ensuring that only that customer can access the infrastructure. This model offers the highest level of security as the customer has complete control over the infrastructure. However, it can be more expensive than multi-tenant architecture, and the customer is responsible for managing and securing the infrastructure. Multi-tenant architecture is when multiple customers share the same infrastructure, with each customer's data and applications separated logically from other customers. This model is cost-effective, but can increase the risk of unauthorized access or data leakage if not properly secured. Hybrid architecture uses public and private cloud infrastructure. This model provides greater flexibility and control over sensitive data and applications by allowing customers to store sensitive data on private cloud infrastructure while using public cloud infrastructure for less sensitive workloads. However, it also requires careful management to ensure proper integration and security between the public and private clouds. Serverless architecture is when the cloud provider manages the infrastructure and automatically scales resources up or down based on demand. This model can be more secure than traditional architectures because the cloud provider manages and secures the infrastructure. However, customers must still take steps to secure access to their applications and data. Hybrid cloud. A hybrid cloud most commonly describes a computing environment combining public and private cloud infrastructures, although any combination of cloud infrastructures constitutes a hybrid cloud. In a hybrid cloud, companies can store data in a private cloud but also leverage the resources of a public cloud when needed. This allows for greater flexibility and scalability, as well as cost savings. A hybrid cloud is commonly used because it enables companies to take advantage of the benefits of both private and public clouds. Private clouds can provide greater security and control over data, while public clouds offer more cost-effective scalability and access to a broader range of resources. A hybrid cloud also allows for a smoother transition to the cloud for companies that may need more time to migrate all of their data. A hybrid cloud also presents security challenges, such as managing multiple cloud environments and enforcing consistent security policies. One issue is the complexity of managing multiple cloud environments and integrating them with on-premises infrastructure, which can create security gaps and increase the risk of data breaches. Another concern is the potential for unauthorized access to data and applications, particularly when sensitive information is stored in the public cloud. There are often mistakes caused by confusion over the boundary between on-premises and public cloud infrastructure. Additionally, using multiple cloud providers can make it challenging to enforce consistent security policies across all environments. A hybrid cloud infrastructure can provide data redundancy features, such as replicating data across on-premises and cloud infrastructure. Data protection can be achieved through redundancy, but it can also lead to issues with data consistency stemming from synchronization problems among multiple locations. Considering that legal compliance is a critical concern when implementing any type of cloud environment, organizations must ensure that data stored in both the on-premises and cloud components of the hybrid environment comply with these mandates. This adds additional complexity to data governance and security operations. Another consideration is the establishment and enforcement of service-level agreements, SLAs. SLAs formally outline all performance, availability, and support expectations between the cloud service provider and the organization. Guaranteeing expected levels of service can be challenging when dealing with the integration of different cloud and on-premises systems. Other concerns related to the hybrid cloud include the potential for increased network latency due to large data transfer volumes between on-premises and cloud environments that impact application performance, and monitoring the hybrid environment can be more complex due to the requirement for specialized expertise and tools. Cloud service models, as well as the ownership model, public, private, hybrid, or community. Cloud service models are often differentiated on their level of complexity and the amount of preconfiguration provided. These models are referred to as something or anything as a service, SaaS. The three most common implementations are infrastructure, software, and platform. Software as a service. Software as a service, SaaS, is a model of provisioning software applications. Rather than purchasing software licenses for a given number of seats, a business accesses software hosted on a supplier's servers on a pay-as-you-go or lease arrangement, on demand. The virtual infrastructure allows developers to provision on-demand applications much more quickly than previously. The applications are developed and tested in the cloud without the need to test and deploy on client computers. Examples include Microsoft Office 365, Microsoft.com/and-Microsoft-365/enterprise, Salesforce, Salesforce.com, and Google Workspace, Workspace, Google.com. Platform as a Service. Platform as a Service, PaaS, provides resources somewhere between SaaS and IaaS. A typical PaaS solution would provide servers and storage network infrastructure, as per IaaS, but also provide a multi-tier web application/database platform on top. This platform could be based on Oracle and MS SQL or PHP and MySQL. Examples include Oracle Database, oracle.com/database, Microsoft Azure SQL Database, Azure, Microsoft com/services/SQL-database, and Google App Engine, Cloud, google.com/app engine. Distinct from SaaS, this platform would not be configured to do anything. Your developers would create the software, the CRM or e-commerce application, that runs using the platform. The service provider would be responsible for the integrity and availability of the platform components, and you would be responsible for the security of the application you created on the platform. Infrastructure as a Service. Infrastructure as a Service, IaaS, is a means of provisioning IT resources such as servers, load balancers, and storage area network (SAN) components quickly. Rather than purchase these components and the internet links they require, you rent them as needed from the service provider's data center. Examples include Amazon Elastic Compute Cloud, AWS, Amazon.com/EC2, Microsoft Azure Virtual Machines, Azure, Microsoft com/services/virtual-machines, Oracle Cloud, oracle.com/cloud, and OpenStack, openstack.org. Third-party vendors. Third-party vendors are external entities that provide organizations with goods, services, or technology solutions. In cloud computing, third-party vendors refer to the providers offering cloud services to businesses using infrastructure platform or software as a service models. As a third party, careful consideration regarding cloud service provider selection, contract negotiation, service performance, compliance, and communication practices is paramount. Organizations must adopt robust vendor management strategies to mitigate cloud platform risks, ensure service quality, and optimize cloud deployments. Service Level A. Agreements, SLAs, are contractual agreements between organizations and cloud service providers that outline the expected levels of service delivery. SLAs define metrics such as uptime, performance, and support response times, along with penalties or remedies if service levels are not met. SLAs provide a framework to hold vendors accountable for delivering services at required performance levels. Organizations must assess the security practices implemented by vendors to protect their sensitive data, including data encryption, access controls, vulnerability management, incident response procedures, and regulatory compliance, and are responsible for ensuring compliance with data privacy requirements, especially if they handle personally identifiable information (PII) or operate in regulated industries. Vendor lock-in makes switching to alternative vendors or platforms challenging or impossible, and so organizations must carefully evaluate data portability, interoperability, and standardization to mitigate vendor lock-in risks. Strategies like multi-cloud or hybrid cloud deployments can provide flexibility and reduce reliance on a single vendor. Responsibility matrix. When using cloud infrastructure, security risks are not transferred but shared between the cloud provider and the customer. The cloud provider is responsible for securing the underlying infrastructure, while the customer is responsible for securing their applications and data. Choosing a cloud provider that offers robust security features such as encryption, access controls, and network security is important. The shared responsibility model describes the balance of responsibility between a customer and a cloud service provider, CSP, for implementing security in a cloud platform. The division of responsibility becomes more or less complicated based on whether the service model is SaaS, PaaS, or IaaS. For example, in a SaaS model, the CSP performs the operating system configuration and control as part of the service offering. In contrast, operating system security is shared between the CSP and the customer in an IaaS model. A responsibility matrix sets out these duties in a clear, tabular format.
Description.
The column headers read Responsibility, On-Premises, IaaS, PaaS, SaaS, FOSS, CS Controls Cloud Companion Guide, and CS Foundations Benchmarks. The data are as follows. Data classification and accountability. Cloud customer for on-premises, IaaS, PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, yes. CS Foundations Benchmarks, yes. Client and endpoint protection. Cloud customer for on-premises, IaaS, and PaaS. Both cloud customer and cloud provider for SaaS and FOSS. CS Controls Cloud Companion Guide, yes. CS Foundations Benchmarks, yes. Identity and access management. Cloud customer for on-premises and IaaS. Both cloud customer and cloud provider for PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, yes. CS Foundations Benchmarks, yes. Application level controls. Cloud customer for on-premises and IaaS. Both cloud customer and cloud provider for PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, yes. CS Foundations Benchmarks, yes. Network controls. Cloud customer for on-premises. Both cloud customer and cloud provider for loss. Cloud provider for PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, yes. CS Foundations Benchmarks, yes. Host infrastructure. Cloud customer for on-premises. Both cloud customer and cloud provider for loss. Cloud provider for PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, yes.
CS Foundations Benchmarks, no.
Physical security. Cloud customer for on-premises. Cloud provider for loss, PaaS, SaaS, and FOSS. CS Controls Cloud Companion Guide, no.
CS Foundations Benchmarks, no.
Responsibility model. Function as a service, FOSS, is associated with serverless computing. It allows developers to execute individual pieces of code or functions in response to various triggers, such as HTTP requests, database changes, or scheduled tasks. The function can be scaled dynamically to handle changes in load, similarly to other cloud-based services. In general terms, the responsibilities of the customer and the cloud provider include the following areas. Cloud service provider. Physical security of the infrastructure. Securing computer, storage, and network equipment. Securing foundational elements of networking, such as DDoS protection. Cloud storage backup and recovery. Security of cloud infrastructure resource isolation among tenants. Tenant resource identity and access control. Security, monitoring, and incident response for the infrastructure. Securing and managing the data centers located in multiple geographic regions. Cloud service customer. User identity management. Configuring the geographic location for storing data and running services. User and service access controls to cloud resources. Data and application security configuration. Protection of operating systems when deployed. Use and configuration of encryption, especially the protection of keys. As previously stated, the division of responsibility becomes more/less complicated based on the service model used. For example, in a SaaS model, the configuration and control of networking is performed by the CSP as part of the service offering. In an IaaS model, the responsibility for network configuration is shared between the CSP and the customer. An important core concept when using cloud resources is that the implementation and management of security controls is not a hands-off endeavor, and identifying the boundary between customer and CSP responsibilities requires a conscious effort. Identifying the boundary between customer and cloud provider responsibilities in terms of security is imperative for reducing the risk of introducing vulnerabilities into your environment. Centralized and decentralized computing. Centralized computing architecture refers to a model where all data processing and storage is performed in a single location, typically a central server. All users and devices rely on the central server to access and process data and depend upon the server administrator and controlling organization's trustworthiness regarding security and privacy decisions. Examples of centralized computing architecture include mainframe computers and client-server architectures. In contrast, decentralized computing architecture is a model in which data processing and storage are distributed across multiple locations or devices. No single device or location is responsible for all data processing and storage. Decentralized computing architectures are an increasingly important design trend impacting modern infrastructures. The choice between centralized and decentralized architecture depends on an organization's specific needs and goals. Centralized architecture is often used in large organizations with a need for strict control and management. In contrast, decentralized architecture is used in situations where resilience and flexibility are more important than central control. Decentralized architecture is becoming increasingly popular as it offers several benefits, such as improved fault tolerance, scalability, and unique security features. Some noteworthy examples of decentralized architecture include the following. Blockchain is a distributed ledger technology that allows for secure, transparent, and decentralized transactions. Peer-to-peer, P2P, networks are networks designed to distribute processing and data storage among participating nodes instead of relying on a central server. Content delivery networks, CDNs, distribute content across multiple servers to improve performance, reliability, and scalability. Internet of Things, IoT, devices can be connected in a decentralized network to share data and processing power. Distributed databases distribute data across multiple servers, ensuring that data is always available, even if one server goes down. Tor, the onion router, is a network that enables anonymous communication and browsing. Tor routes traffic through a network of volunteer-operated servers, or nodes, to hide a user's location and internet activity. Resilient architecture concepts. One of the benefits of the cloud is the potential to provide services resilient to failures at different levels, such as components, servers, local networks, sites, data centers, and wide area networks. The CSP uses a virtualization layer to ensure that computer, storage, and network provisions meet the availability criteria set out in its SLA. In terms of storage performance tiers, high availability, HA, refers to storage provisioned with a guarantee of 99.99% uptime or better. As with on-premises architecture, the CSP uses redundancy to make multiple disk controllers and storage devices available to a pool of storage resources. Data may be replicated between pools or groups, with each pool supported by separate hardware resources. Replication. Data replication allows businesses to copy data to where it can be utilized most effectively. The cloud may be used as a central storage area, making data available among all business units. Data replication requires low-latency network connections, security, and data integrity. CSPs offer several data storage performance tiers. Cloud, google.com/storage/docs/storage-classes. The terms hot storage and cold storage refer to how quickly data is retrieved. Hot storage retrieves data more quickly than cold, but the quicker the data retrieval, the higher the cost. Different applications have diverse replication requirements. A database generally needs low latency, synchronous replication, as a transaction often cannot be considered complete until it has been made on all replicas. A mechanism to replicate data files to backup storage might not have such high requirements, depending on the criticality of the data. High availability across zones. CSPs divide the world into regions. Each region is independent of the others. The regions are divided into availability zones. The availability zones have independent data centers with their own power, cooling, and network connectivity. You can choose to host data, services, and VM instances in a particular region to provide a lower latency service to customers. Provisioning resources in multiple zones and regions can also improve performance and increases redundancy, but it requires an adequate level of replication performance. Consequently, CSPs offer several tiers of replication representing different high availability service levels. Local replication replicates your data within a single data center in the region where you created your storage account. The replicas are often in separate fault domains and upgrade domains. Regional replication, also called zone redundant storage, replicates your data across multiple data centers within one or two regions. This safeguards data and access in the event a single data center is destroyed or goes offline. Geo-redundant storage, GRS, replicates your data to a secondary region that is distant from the primary region. This safeguards data in the event of a regional outage or a disaster. Rate your application virtualization and container virtualization. Application virtualization is a more limited type of virtual desktop infrastructure, VDI. Rather than run the whole client desktop as a virtual platform, the client either accesses an application hosted on a server or streams the application from the server to the client for local processing. Most application virtualization solutions are based on Citrix XenApp, formerly MetaFrame Presentation Server, though Microsoft has developed an AppV product with its Windows Server range and VMware has the ThinApp product. These solution types are often used with HTML5 remote desktop apps, referred to as clientless, because users can access them through ordinary web browser software. Containerization is a powerful technology that has transformed application packaging and deployment. Containers encapsulate all necessary components for software, including code, libraries, and configurations, within a portable unit termed a container. Isolating software in this way ensures consistent application behavior regardless of the underlying platform on which it runs. Software containers parallel the use of physical containers utilized in the shipping industry. For example, all components required to deliver a web application could be deployed in containers and managed using a container platform such as Docker. Docker represents the cargo ship used to hold the containers. This differs significantly from installing the components from a code repository directly into the operating system and manually editing all associated configuration files. By leveraging containers, different application components can be swapped, avoiding many complexities associated with traditional software installation and configuration. Traditional methods frequently encounter issues because the target system's configuration has different versions of software and libraries needed by the new components. A dependency nightmare often manifests as a frustrating cycle of attempting to resolve conflicts by updating or downgrading dependencies, only to encounter new issues or break existing functionality in the process. This wastes time and effort for developers navigating through a maze of dependencies. Containerized applications avoid this because they are self-contained units, each holding an independent copy of its dependencies. Hypervisors play a critical role in virtualization by managing multiple virtual machines, VMs, on a single hardware platform. There are two main types of hypervisors, Type 1 and Type 2. Type 1 hypervisors, also known as bare metal hypervisors, run directly on the physical hardware, offering high performance and efficiency, which makes them ideal for enterprise environments. Examples include VMware ESG and Microsoft Hyper-V, Type 2 hypervisors, or hosted hypervisors, run on top of a host operating system and are often used for development and testing purposes. Examples of Type 2 hypervisors include VMware Workstation and Oracle VirtualBox.
Description.
The first part representing VMs has 6 layers. The 3 layers from the bottom are server, host OS, and hypervisor, Type 2. The next 3 layers are divided into 3 parts each. The 4th layer is divided into 3 guest OS, the 5th layer into 3 bins/libs, and the 6th into App A, App A Prime, and App B. The top 3 layers are collectively labeled VM. The second part representing containers has 5 layers. The 3 layers from the bottom are server, host OS, and Docker Engine. The 4th layer is divided into 2 unequal sections labeled bins/libs. The 5th layer at the top is divided into App A, App A Prime, App B, App B Prime, App B Prime, App B Prime, and App B Prime. Comparison of VMs versus containers. Rate your confidence.
Continue.
Cloud architecture. Serverless computing. Serverless computing is a cloud computing model in which the cloud provider manages the infrastructure and automatically allocates resources as needed, charging only for the actual usage of the application. In this approach, organizations do not need to manage servers and other infrastructure, allowing them to focus on developing and deploying applications. Some examples of serverless computing applications include chatbots designed to simulate conversations with human users to automate customer support, sales, marketing tasks, and mobile backends. These are comprised of the server-side components of mobile applications designed to provide data processing, storage, communication services, and event-driven processing that respond to events or triggers in real time, such as sensor readings, alerts, or other similar events. Major cloud providers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud offer serverless computing capabilities, making it easier for organizations to leverage this technology. Serverless computing provides a scalable, cost-effective, and easy-to-manage infrastructure for event-driven and data processing tasks. With serverless, all the architecture is hosted within a cloud, but unlike traditional virtual private cloud, VPC, offerings, services such as authentication, web applications, and communications aren't developed and managed as applications running on VM instances within the cloud. Instead, the applications are developed as functions and microservices, each interacting with other functions to facilitate client requests. Billing is based on execution time rather than hourly charges. Examples of this type of service include AWS Lambda, AWS Amazon.com/Lambda, Google Cloud Functions, Cloud, Google.com/Functions, and Microsoft Azure Functions, Azure, Microsoft.com/services/functions. Serverless platforms eliminate the need to manage physical or virtual server instances, so there is little to no management effort for software and patches, administration privileges, or file system security monitoring. There is no requirement to provision multiple servers for redundancy or load balancing. As all of the processing is taking place within the cloud, there is little emphasis on the provision of a corporate network. The service provider manages this underlying architecture. The principal network security job is to ensure that the clients accessing the services have not been compromised. Serverless architecture depends heavily on event-driven orchestration to facilitate operations. For example, multiple services are triggered when a client connects to an application. The application needs to authenticate the user and device, identify the location of the device and its address properties, create a session, load authorizations for the action, use application logic to process the action, read or commit information from a database, and log the transaction. This design logic differs from applications written in a monolithic, server-based environment. Microservices. Microservices is an architectural approach to building software applications as a collection of small and independent services, focusing on a specific business capability. Each microservice is designed to be modular, with a well-defined interface and a single responsibility. This approach allows developers to build and deploy complex applications more efficiently by breaking them down into smaller, more manageable components. Microservices also enable teams to work independently on different application features, making it easier to scale and update individual components without affecting the entire system. Overall, microservices promise to help organizations build more agile, scalable, and resilient applications that adapt quickly to changing business needs. Risks associated with this model are largely attributed to integration issues. While individual components operate well independently, they often reveal problems difficult to isolate and resolve once they are integrated. Microservices and infrastructure as code, IAC, are related technologies, and microservices architecture is often implemented using IAC practices. Using IAC, developers can define and deploy infrastructure as code, ensuring consistency and repeatability across different environments. This allows for more efficient development and deployment of microservices since developers can independently automate the provisioning and deploying infrastructure for each microservice. Transformational changes. Cloud computing offers many unique architectural services that differ from traditional on-premises services. Cloud-native services allow organizations to scale, innovate, and optimize their operations like never before. Important cloud architectural services include offerings like elastic compute and autoscaling, which enable dynamic shifts in computing power in response to demand fluctuations. Other services, such as serverless computing, significantly change application development practices by abstracting traditional server resources. Additionally, cloud platforms provide advanced content delivery networks, CDN, that optimize web traffic by caching content, and object storage provides massive, unstructured data storage services that often replace traditional file servers. Identity and access management tools provide advanced security features and enable new methods of platform integration, while containerization and container orchestration tools are changing how applications are deployed and managed. AI and machine learning services, serverless databases, backend IoT services, and big data analytics capabilities further expand the range of possibilities for organizations utilizing the cloud. These cloud architectural services provide unprecedented potential to large and small organizations. However, while these services are undoubtedly driving transformative innovation, the rate of change and unfamiliar risks present in cloud platforms fuel significant new security issues and record-breaking data breaches. Cloud automation technologies. Infrastructure as code. Infrastructure as code, IAC, is a software engineering practice that manages computing infrastructure using machine-readable definition files. These files contain code written in a specific format that can be read and executed by machines. These files manage and provision computing infrastructure. Machine-readable definition files are written in formats like YAML, JSON, and HCL, HashiCorp configuration language. They contain information about the desired infrastructure state, including configuration settings, networking requirements, security policies, and other settings. By using machine-readable definition files, infrastructure can be deployed and managed automatically and consistently, reducing the risk of errors caused by manual intervention. These files are typically version-controlled and can be treated like any other code in a software project. IAC allows developers and operations teams to automate the process of deploying and managing infrastructure, reducing the likelihood of errors and inconsistencies that can arise from manual configuration. By using IAC, teams can also easily replicate infrastructure across different environments, such as development, staging, and production, and ensure that their infrastructure configuration is consistent and reproducible. HCL, HashiCorp Configuration Language, is a configuration language developed by HashiCorp and used in infrastructure as code, IAC, environments to manage and provision computing infrastructure. HCL is similar to JSON and YAML in terms of syntax, but it has some additional features that make it more suitable for infrastructure management. It supports variables inside configuration files and has a concise syntax that makes it easy to read and write. HCL is used in many popular HashiCorp tools, including Terraform and Consul. Responsiveness. Load balancing, edge computing, and auto-scaling are critical mechanisms to ensure responsiveness, improve performance, and effectively handle fluctuating workloads. Load balancing distributes network traffic across multiple servers or services to improve performance and provide high availability. In the cloud, load balancers are intermediaries, proxies, between users and backend resources like virtual machines or containers. They distribute incoming requests to different resources using sophisticated algorithms and handle server capacity, response time, and workload. Edge computing optimizes the geographic location of resources and services to enable faster processing and reduce latency. Instead of routing all data to a centralized cloud data center, edge computing utilizes distributed computing resources to minimize the distance data needs to travel, reducing network latency and improving responsiveness. Edge computing is particularly beneficial for applications that require real-time or low-latency processing, such as IoT devices, content delivery networks, CDNs, and latency-sensitive applications. Autoscaling is an automated process that adjusts the computing resources allocated to an application based on demand. Autoscaling allows cloud infrastructure to dynamically scale resources up or down to match the real-time workload requirements. For example, during periods of high demand, additional resources are provisioned automatically to handle the increased load, ensuring optimal performance and responsiveness. In contrast, when demand decreases, unnecessary resources are released back into a shared pool to reduce operating costs or to make them available to other workloads. These mechanisms optimize resource utilization, reduce latency, and allow infrastructure to adapt on demand to changing workload patterns, resulting in a highly responsive and efficient cloud environment. Rate your software-defined networking. IAC is partly facilitated by physical and virtual network appliances that are fully configurable via scripting and APIs. As networks become more complex, perhaps involving thousands of physical and virtual computers and appliances, it becomes more difficult to implement network policies, such as ensuring security and managing traffic flow. With so many devices to configure, it is better to take a step back and consider an abstract model of how the network functions. In this model, network functions can be divided into three planes. Management plane monitors traffic conditions and network status. Control plane makes decisions about how traffic should be prioritized, secured, and where it should be switched. Data plane handles the switching and routing of traffic and imposition of security access controls. A software-defined networking (SDN) application can be used to define policy decisions on the control plane. These decisions are then implemented on the data plane by a network controller application, which interfaces with the network devices using APIs. The interface between the SDN applications and the SDN controller is described as the northbound API, while that between the controller and appliances is the southbound API. SDN can be used to manage compatible physical appliances, but also virtual switches, routers, and firewalls. The architecture supporting the rapid deployment of virtual networking using general-purpose VMs and containers is called Network Functions Virtualization, NFV, read@.com/topics/virtualization/ what dash is dash NFV. This architecture saves network and security administrators the job and complexity of configuring appliance settings properly to enforce a desired policy. It also allows for fully automated deployment or provisioning of network links, appliances, and servers. This makes SDN an important part of the latest automation and orchestration technologies.
Description.
The software-defined network, SDN, has a management plane at the top that includes people. The management plane monitors the control plane, which monitors the routers in the data plane. Data plane devices managed by a control plane device and monitored by a management plane. Cloud architecture features. Public cloud infrastructure provides a wide range of available features to ensure high uptime and minimal downtime for its customers. Data replication and redundancy are among the key features, as public cloud providers replicate data across multiple servers and data centers to ensure data availability in the event of a server or data center failure. Auto-scaling is also a critical feature that allows resources to scale automatically based on demand, ensuring that applications can handle high traffic volumes without downtime. Public cloud providers offer disaster recovery services, including monitoring and alerting tools, to proactively detect and respond to any issues that could impact availability. Public cloud providers also typically offer service level agreements, SLAs, that guarantee a certain level of uptime and availability, including credits or refunds if the provider fails to meet availability commitments. Considerations. Cost should focus on solutions that best achieve operational goals while maintaining the confidentiality, integrity, and availability of data, not simply cost in cloud adoption. There are several cost models associated with running services in the cloud, such as consumption-based or subscription-based, and most cloud providers have tools designed to help estimate costs for migrating existing workloads from on-premises to cloud. Using cloud services involves a shift from capital expenses, CapEx, to operational expenses, OpEx. CapEx includes upfront costs for purchasing hardware, software licenses, and infrastructure setup in traditional on-premises IT infrastructure. In contrast, cloud services are typically paid on a pay-as-you-go basis, allowing organizations to convert CapEx into OpEx. Cloud services charge for usage and resource consumption, eliminating the need for significant upfront investments. This OpEx model provides flexibility, scalability, and cost optimization as organizations pay only for the resources they use, making cloud services more cost-effective from the viewpoint that they align expenses with actual usage. However, resources not optimized to run on cloud infrastructure can present significant challenges to the benefits this model advertises and generate overbearing recurring costs. Scalability is one of the most valuable and compelling features of cloud computing. It is the ability to dynamically expand and contract capacity in response to demand with no downtime. There are two basic ways in which services can be scaled. Scale-up, vertical scaling, describes adding capacity to an existing resource, such as a processor, memory, and storage capacity. Scale-out, horizontal scaling, describes adding additional resources, such as more instances or virtual machines, to work in parallel and increase performance. Resilience. Cloud providers use redundant hardware, fault tolerance capabilities such as clustering, and data replication to store data across multiple servers and data centers, ensuring that data remains available if one server or data center fails. Ease of deployment. Cloud features supporting ease of deployment include automation, standardization, and portability. Automating the deployment and management of cloud resources reduces the need for manual intervention and is often achieved using configuration management, container orchestration, and infrastructure as code. Standardized configurations, templates, and images simplify deployment and ensure consistency. Portability ensures that applications and services can be easily moved between different cloud infrastructures, avoiding vendor lock-in and providing greater flexibility. Ease of recovery. Cloud providers typically offer backup and restore functionality to allow organizations to schedule automated backups and quickly restore data in case of accidental deletion, corruption, or system failures. Cloud providers often implement highly redundant and fault-tolerant architectures, distribute data and services across multiple data centers or availability zones, and reduce the risk of data loss or service disruption by ensuring that workloads seamlessly fail over if one data center or zone experiences an outage. Additionally, cloud providers offer disaster recovery services that enable organizations to replicate their environments in different geographic regions to provide failover capabilities in the event of a catastrophe. SLA and ISA, Service Level Agreements, SLAs, define expected service levels, including performance, availability, and support commitments between cloud service providers and organizations. It is essential to carefully review and negotiate SLAs to ensure they align with business requirements and adequately protect the organization's interests. Interconnection Security Agreements, ISAs, establish the security requirements and responsibilities between the organization and the cloud service provider to safeguard sensitive data and ensure compliance with industry regulations to help ensure the confidentiality, integrity, and availability of data and systems within the cloud environment. ISAs help ensure data and system protection within the cloud environment and define encryption methods, access controls, vulnerability management, and data segregation techniques. The agreement must also specify data ownership, audit rights, and data backup, recovery, and retention procedures. Regulated industries must ensure that their cloud service provider complies with relevant regulations, such as GDPR, HIPAA, or PCI DSS, and the ISA must detail how the provider meets these compliance requirements and include provisions for auditing and reporting to demonstrate ongoing compliance. Additionally, the ISA should address the use of subcontractors and clearly define the security responsibilities and requirements for their selection and the process for notifying the organization of subcontractor changes. Disaster recovery planning is still essential and should include procedures for restoring critical systems, data, and applications, and communicating with customers and other stakeholders. Additionally, testing and validation, service level agreements, and incident response procedures must all be carefully considered when evaluating the ease of recovery of cloud infrastructure. Power. Cloud providers prioritize energy efficiency to reduce costs and environmental impact by deploying energy-efficient hardware, optimizing cooling systems, and implementing power management techniques. Additionally, redundant power infrastructure ensures high availability and is enabled using multiple power feeds, backup generators, and UPS systems to prevent service disruptions. Power monitoring and management systems enable cloud providers to track real-time power consumption within data centers. These systems can help to optimize resource allocation, identify energy-intensive infrastructure, and facilitate load balancing. Scalability in power provisioning refers to a provider's ability to dynamically allocate power resources based on customer demand.
Power usage, E.
Effectiveness, PUE, is a metric used to measure data center energy efficiency. Cloud providers strive for low PUE values, indicating efficient utilization of energy. A lower PUE signifies that a larger proportion of the energy supplied to the data center is used for computing purposes rather than supporting infrastructure.
Compute.
Compute capabilities in cloud architecture provide the flexibility, scalability, and efficiency necessary to manage and utilize computing resources. Compute capabilities include elasticity, resource pooling, orchestration, automation, and serverless computing, which contribute to delivering highly available, scalable, and cost-effective computing environments in the cloud. Virtual networks facilitate secure communication and traffic routing, while load balancing distributes network traffic to optimize resource utilization and improve performance. Networking also enables private and public connectivity, allowing organizations to establish secure connections between on-premises infrastructure and cloud resources and enabling external access to cloud-based applications. Additionally, networking supports scalable and distributed architectures, enabling fault tolerance, high availability, and efficient content delivery through specialized services such as Content Delivery Networks, CDNs. Cloud security considerations. Data protection. Data and applications are stored outside of an organization's privately managed infrastructure and are essentially stored on the internet, which means that configuration mistakes can have disastrous consequences. Taking careful precautions to protect data using access controls and encryption is essential. Additionally, disaster recovery plans must still be developed in response to any catastrophic events that impact the availability of cloud resources. Patching. Cloud providers should have a clear policy regarding patch management, including how often patches are released and how quickly the provider will respond to critical vulnerabilities. Additionally, it's essential to consider how easy it is to apply patches to applications and systems running on the cloud infrastructure. Patch availability can be ensured through various features, including automated patch management, regular software updates, centralized patch management, security monitoring, third-party software support. Having a plan for testing and deploying patches ensures systems do not experience unplanned downtime and remain secure. Several factors can make patching cloud infrastructures difficult or even impossible to accomplish consistently. One common challenge is the complexity of cloud systems, which can make it difficult to identify and address vulnerabilities. Additionally, some cloud providers may not allow customers to modify the underlying infrastructure, making it impossible to install patches directly. In a cloud environment, the cloud service provider manages the underlying infrastructure. This lack of control can make it difficult or even impossible to apply patches according to legal and regulatory requirements or timelines. Secure communication and access. A software-defined wide area network, SD-WAN, enables organizations to connect their various branch offices, data centers, and cloud infrastructure over a wide area network, WAN. One of the key advantages of SD-WAN is its ability to provide enhanced security features and considerations. For example, SD-WAN uses encryption to protect data as it travels across the network and can segment network traffic based on priority ratings to ensure that critical data is fully protected. Additionally, SD-WAN can intelligently route traffic based on the application and tightly integrate with firewalls to provide additional protection against known threats. SD-WAN centralizes the management of network security policies to simplify enforcing security measures across an entire network. Secure Access Service Edge (SASE) combines the protection of a secure access platform with the agility of a cloud-delivered security architecture. SASE offers a centralized approach to security and access, providing end-to-end protection and streamlining the process of granting secure access to all users, regardless of location. SASE is a network architecture that combines wide area networking, WAN, technologies, and cloud-based security services to provide secure access to cloud-based applications and services. SASE offers several security features to help organizations protect their networks and data as SASE operates under a zero-trust security model. SASE incorporates identity and access management, IAM, and assumes all users and devices are untrusted until they are authenticated and authorized. SASE also provides a range of threat prevention features, such as intrusion prevention, malware protection, and content filtering. Rate your confidence. Exam objectives covered. 1.2 Summarize fundamental security concepts. 3.1 Compare and contrast security implications of different architecture models. As security professionals, it is essential to understand concepts related to embedded systems, the Internet of Things, IoT, industrial controls, and zero-trust architecture. As the adoption of embedded systems and IoT devices continue to increase across industries, they introduce new and unique security challenges. Understanding these technologies is crucial for implementing appropriate security measures, ensuring resilience, and maintaining the integrity of critical infrastructures. Security professionals must also be well-versed in zero-trust concepts, emphasizing the never trust, always verify principle. Knowledge of these concepts empowers security professionals to mitigate risks in an increasingly complex and interconnected world. Rate Embedded systems. Embedded systems are used in various specialized applications, including consumer electronics, industrial automation, automotive systems, medical devices, and more. Some examples include the following. Home appliances, such as refrigerators, washing machines, and coffee makers, contain embedded systems that control their functions and operations. Smartphones and tablets contain a variety of embedded systems, including processors, sensors, and communication modules. Automotive systems, like modern cars, contain embedded systems including engine control units, entertainment systems, and safety systems like airbags and anti-lock brakes. Industrial automation. Embedded systems exist in control systems and machinery such as robots, assembly lines, and sensors. Medical devices such as pacemakers, insulin pumps, and blood glucose monitors. Aerospace and defense, like aircraft, satellites, and military equipment, use embedded systems for navigation, communication, and control. Real-time operating systems. A real-time operating systems, RTOS, is a type of operating system designed for use in applications that require real-time processing and response. They are purpose-specific operating systems designed for high levels of stability and processing speed. Examples of RTOS. The VxWorks operating system is commonly used in aerospace and defense systems. VxWorks provides real-time performance and reliability and is therefore well suited for use in aircraft control systems, missile guidance systems, and other critical defense systems. Another example of an RTOS is FreeRTOS, an open-source operating system used in many embedded systems, such as robotics, industrial automation, and consumer electronics. In the automotive industry, RTOS is used in engine control, transmission control. In industrial control systems, transmission control, and active safety systems applications. For example, the AUTOSAR, Automotive Open System Architecture, standard defines a framework for developing automotive software, including using RTOS for certain applications. In medical devices, RTOS is used for applications such as patient monitoring systems, medical imaging, and automated drug delivery systems. In industrial control systems, RTOS is used for process control and factory automation applications. For example, the Siemens Simatic WinCC open architecture system uses RTOS to provide real-time performance and reliability for industrial automation applications. Risks associated with RTOS. A security breach involving RTOS can have serious consequences. RTOS software can be complex and difficult to secure, which makes it challenging to identify and address vulnerabilities that could be exploited by attackers. Another security risk associated with RTOS is the potential for system-level attacks. Rate your confidence. An attacker who gains access to an RTOS-based system could potentially disrupt critical processes or gain control over the system it is designed to control. This can lead to serious consequences considering the types of applications that rely on RTOS, such as medical devices and industrial control systems. A security breach could result in harm to people or damage to equipment. Rate your confidence. Industrial control systems. Workflow and process automation systems. Industrial control systems, ICSs, provide mechanisms for workflow and process automation. These systems control machinery used in critical infrastructure, like power suppliers, water suppliers, health services, telecommunications, and national security services. An ICS that manages process automation within a single site is usually referred to as a distributed control system, DCS. An ICS comprises plant devices and equipment with embedded programmable logic. Supervisory control. Logic controllers, PLCs. The PLCs are linked either by an operational technology, OT, field bus serial network, or by industrial Ethernet to actuators that operate valves, motors, circuit breakers, and other mechanical components, plus sensors that monitor some local state, such as temperature. Output and configuration of a PLC are performed by one or more human-machine interfaces, HMIs. An HMI might be a local control panel or software running on a computing host. PLCs are connected within a control loop, and the whole process automation system can be governed by a control server. Another important concept is the data historian, or a database of all the information the control loop generated. Supervisory control and data acquisition, SCADA. A supervisory control and data acquisition (SCADA) system takes the place of a control server in large-scale, multiple-site ICSs. SCADA typically run as software on ordinary computers, gathering data from and managing plant devices and equipment with embedded PLCs, referred to as field devices. SCADA typically use WAN communications, such as cellular or satellite, to link the SCADA server to field devices. ICS/SCADA applications. These types of systems are used within many sectors of industry. Energy refers to power generation and distribution. More widely, utilities include water/sewage and transportation networks. Industrial can refer specifically to mining and refining raw materials, involving hazardous high heat and pressure furnaces, presses, centrifuges, pumps, and so on. Fabrication and manufacturing refer to creating components and assembling them into products. Embedded systems are used to control automated production systems, such as forges, mills, and assembly lines. These systems must work to extremely high precision. Logistics refers to moving things from where they were made or assembled to where they need to be, either within a factory or for distribution to customers. Embedded technology is used in control of automated transport and lift systems plus sensors for component tracking. Facilities refer to site and building management systems, typically operating automated heating, ventilation, and air conditioning, HVAC, lighting, and security systems. ICS/SCADA was historically built without regard to IT security, though there is now high awareness of the necessity of enforcing security controls to protect them, especially when they operate in a networked environment. One infamous example of an attack on an embedded system is the Stuxnet worm, wired com/2014/11/countdown- to -0-day-stuxnet. This was designed to attack the SCADA management software running on Windows PCs to damage the centrifuges used by Iran's nuclear fuels program. NIST Special Publication 800-82 covers some recommendations for implementing security controls for ICS and SCADA, NVL pubs. NIST gov/NIST pubs/special publications/NIST SP 800-82R2 PDF. Industrial systems have different priorities than IT systems. Often hazardous electromechanical components are involved, so safety is the overriding priority. Industrial processes also prioritize availability and integrity over confidentiality, reversing the CIA triad as the AIC triad. Cybersecurity is paramount in industrial control systems, ICS, and supervisory control and data acquisition, SCADA systems. These systems are associated with critical infrastructure sectors such as energy, manufacturing, transportation, and water treatment. Cyber attacks on these systems can severely impact public safety, economic stability, and national security. ICS and SCADA systems control and monitor critical processes and operational technologies, making them attractive targets for attackers. The consequences of attacks range from widespread power outages and environmental damage to economic losses and even loss of life. Malware, ransomware, unauthorized access, and targeted attacks pose significant risks to ICS and SCADA systems and robust cybersecurity protections, including network segmentation, access controls, intrusion detection systems, encryption, and continuous monitoring, are essential to safeguarding these critical systems. Rate your Internet of Things. The Internet of Things, IoT, refers to the network of physical devices, vehicles, appliances, and other objects embedded with sensors, software, and connectivity, enabling them to collect and exchange data. Sensors are small devices designed to detect changes in the physical environment, such as temperature, humidity, and motion. On the other hand, actuators can perform actions based on data collected by sensors, such as turning on a light or adjusting a thermostat. IoT devices communicate with each other and with other, often public cloud-based, systems over the internet to exchange data and receive instructions. Cloud-based systems form an essential component of IoT infrastructures as they provide the computational power needed to perform data analytics on the large amounts of data generated by IoT devices. IoT examples. There are many IoT devices and applications in use today. For example, smart homes often use IoT sensors and actuators to control lighting, temperature, and security systems, allowing homeowners to monitor and adjust their homes remotely. Smart cities also use IoT to manage traffic, monitor air quality, and improve public safety. In the healthcare industry, IoT devices such as wearables and implantable devices can collect data on patient health and send it to healthcare providers for analysis. In agriculture, IoT sensors are used to monitor soil conditions, weather patterns, and crop growth, helping farmers make more informed decisions about planting and harvesting. IoT devices are used to improve efficiency, convenience, and quality of life in a wide range of industries and applications. Factors driving adoption of IoT. Several factors drive the rapid adoption of IoT. The significantly decreased cost of IoT sensors and devices over the past few years has made them more affordable and accessible to businesses and consumers. This has enabled the development of a wide range of IoT applications and services that were previously too expensive to implement. Advances in connectivity technology, such as 5G and low-power wireless networks, have made connecting and managing large numbers of IoT devices easier and more efficient. This has also improved the speed and reliability of data transmission, enabling real-time monitoring and response. The proverbial explosion of data generated by IoT devices has led to new data analytics tools and techniques, such as machine learning and artificial intelligence, that help organizations analyze vast amounts of data and extract valuable insights. The COVID-19 pandemic has accelerated the adoption of IoT in many industries, particularly in healthcare, where remote monitoring and telemedicine have become increasingly important. As more organizations recognize the value of IoT, adoption is likely to continue to grow in the coming years. Security risks associated with IoT. There are several significant security risks associated with IoT. One major risk is the large number of IoT devices deployed without adequate security measures. Many IoT devices are designed with limited processing power and memory, making it difficult to implement strong security controls. This can make them vulnerable to cyber attacks, compromising data privacy, system integrity, and physical safety. Another risk is the need for more standardization in IoT devices and protocols. Compatibility issues can make integrating different IoT devices and services difficult. It can also make implementing security controls more difficult, as different devices may have different security requirements and protocols, making them incompatible. The sheer volume of data generated by IoT devices can make securing and protecting sensitive information difficult. As more devices are connected to the internet, there is an increasing risk of data breaches and cyber attacks, which can result in the theft of personal and sensitive data. Examples of security issues caused by implementing or using IoT include the Mirai botnet attack, which infected millions of IoT devices and used them to launch massive distributed denial of service, DDoS, attacks on websites and online services. In another case, a casino was hacked through a smart thermometer in a fish tank, which was used as a backdoor to access the casino's network. There have also been cases of IoT devices being hacked to spy on individuals, such as baby monitors and home security cameras. Casino gets hacked through its internet-connected fish tank thermometer. https://thehackernews.com/2018/0/IoT-hacking-thermometer. HTML. IoT devices often have poor security characteristics for several reasons. IoT devices are typically designed to focus on functionality rather than security and have limited processing power and memory, making it difficult to implement strong security controls. Many IoT devices must be low cost, making it challenging for manufacturers to prioritize security features in their design and development process. Many IoT devices are rushed to market without proper security testing, resulting in vulnerabilities that cybercriminals can exploit. Additionally, consumers and organizations need more awareness of the security risks associated with IoT devices. Many users and organizations do not realize that their devices are vulnerable to cyber attacks and may not take the necessary steps to protect themselves, such as changing default passwords or updating firmware. Best practice guidance for IoT. The following provide guidance regarding the secure implementation of IoT. The Internet deperimeterization, and zero trust. The emerging need for zero trust architectures, CTA. Organizations' increased dependence on information technology has driven requirements for services to be always on, always available, and accessible from anywhere. Cloud platforms have become an essential component of technology infrastructures, driving broad software and system dependencies and widespread platform integration. The distinction between inside and outside is gone. For an organization leveraging remote workforces, running a mix of on-premises and public cloud infrastructure, and using outsourced services and contractors, the opportunity for breach is very high. Staff and employees are using computers attached to home networks, or worse, unsecured public Wi-Fi. Critical systems are accessible through various external interfaces and run software developed by outsourced, contracted external entities. In addition, many organizations design their environments to accommodate bring your own device, BYOD. As these trends continue, implementing zero trust architectures will become more critical. Zero trust architectures assume that nothing should be taken for granted and that all network access must be continuously verified and authorized. Any user, device, or application seeking access must be authenticated and verified. Zero trust differs from traditional security models based on simply granting access to all users, devices, and applications contained within an organization's trusted network. NIST SP 800-207 Zero Trust Architecture defines zero trust as cybersecurity paradigms that move defenses from static, network-based perimeters to focus on users, assets, and resources. A zero trust architecture can protect data, applications, networks, and systems from malicious attacks and unauthorized access more effectively than a traditional architecture by ensuring that only necessary services are allowed and only from appropriate sources. Zero trust enables organizations to offer services based on varying levels of trust, such as providing more limited access to sensitive data and systems. NIST Szkoły Podstawowej 800 do 207 https://csrc.nist.gov/publications/detail/ Szkoły Podstawowej Deperimeterization. Deperimeterization refers to a security approach that shifts the focus from defending a network's boundaries to protecting individual resources and data within the network. As organizations adopt cloud computing, remote work, and mobile devices, traditional perimeter-based security models become less effective in addressing modern threats. Deperimeterization concepts advocate for implementing multiple security measures around individual assets, such as data, applications, and services. This approach includes robust authentication, encryption, access control, and continuous monitoring to maintain the security of critical resources, regardless of their location. Trends driving deperimeterization. Cloud, enterprise infrastructures are typically spread between on-premises and cloud platforms. In addition, cloud platforms may be used to distribute computing resources globally. Remote work. More and more organizations have adopted either part-time or full-time remote workforces. This remote workforce expands the enterprise footprint dramatically. In addition, employees working from home are more susceptible to security lapses when they connect from insecure locations and use personal devices. Mobile. Modern smartphones and tablets are often used as primary computing devices as they have ample processor, memory, and storage capacity. More and more corporate data is accessed through these devices as their capabilities expand. Mobile devices and their associated operating systems have varying security features, and many devices are not supported by vendors shortly after release, meaning they cannot be updated or patched. In addition, mobile devices are often lost or stolen. Outsourcing and contracting. Support arrangements often provide remote access to external entities, and this access can often mean that the external provider's network serves as an entry point to the organizations they support. Wireless networks, Wi-Fi. Wireless networks are susceptible to an ever-increasing array of exploits, but oftentimes wireless networks are open and unsecured, or the network security key is well known. The key benefits of a zero-trust architecture. Greater security requires all users, devices, and applications to be authenticated and verified before network access. Better access controls include more stringent limits regarding who or what can access resources and from what locations. Improved governance and compliance limit data access and provide greater operational visibility on user and device activity. Increased granularity grants users access to what they need when they need it. A zero-trust architecture requires a thorough understanding of the many components and technologies used within an organization's network. The following list outlines the essential components of a zero-trust architecture. Network and endpoint security controls access to applications, data, and networks. Identity and access management, IAM, ensures only verified users can access systems and data. Policy-based enforcement restricts network traffic to only legitimate requests. Cloud security manages access to cloud-based applications, services, and data. Network visibility analyzes network traffic and devices for suspicious activity. Network segmentation controls access to sensitive data and capabilities from trusted locations. Data protection controls and secures access to sensitive data, including encryption and auditing. Threat detection and prevention identifies and prevents attacks against the network and the systems connected to it. Zero Trust Security Concepts. Zero Trust is a security model that assumes that all devices, users, and services are not inherently trusted, regardless of whether inside or outside a network's perimeter. Instead, the Zero Trust model requires all users and devices to be authenticated and authorized before accessing network resources. The Zero Trust model includes several fundamental concepts that provide a comprehensive security solution. Adaptive identity recognizes that user identities are not static and that identity verification must be continuous and based on a user's current context and the resources they are attempting to access. Threat scope reduction means that access to network resources is granted on a need-to-know basis, and access is limited to only those resources required to complete a specific task. This concept reduces the network's attack surface and limits the damage that a successful attack can cause. Policy-driven access control describes how access control policies are used to enforce access restrictions based on user identity, device posture, and network context. Device posture refers to the security status of a device, including its security configurations, software versions, and patch levels. In a security context, device posture assessment involves evaluating the security status of a device to determine whether it meets certain security requirements or poses a risk to the network. Significance of control and data planes in zero trust models. In a zero trust architecture, the control and data planes are implemented separately and have different functions.
Description.
The components are as follows. Control plane. 1. The policy engine is configured with inputs to enable it to make dynamic and continuous authentication and authorization decisions. 2. The policy administrator implements an interface for communicating decisions to data plane systems. Data plane. 3. Subjects, users of other services, possess credentials to access resources. 4. Subjects must use client systems to make requests, but these are not implicitly trusted. 5. The policy enforcement point system is the only one trusted to communicate requests and receive decisions from the policy administrator. 6. The policy enforcement point implements encrypted session setup and teardown as directed by the policy administrator. 7. This architecture creates a limited scope and duration implicit trust zone for resource access. Components in NIST's Zero Trust Architecture Framework. The control plane manages policies that dictate how users and devices are authorized to access network resources. It is implemented through a centralized policy decision point. The policy decision point is responsible for defining policies that limit access to resources on a need-to-know basis, monitoring network activity for suspicious behavior, and updating policies to reflect changing network conditions and security threats. The policy decision point is comprised of two subsystems. The policy engine is configured with subject and host identities and credentials, access control policies, up-to-date threat intelligence, behavioral analytics, and other results of host and network security scanning and monitoring. This comprehensive state data allows it to define an algorithm and metrics for making dynamic authentication and authorization decisions on a per-request basis. The policy administrator is responsible for managing the process of issuing access tokens and establishing or tearing down sessions based on the decisions made by the policy engine. The policy administrator implements an interface between the control plane and the data plane. Where systems in the control plane define policies and make decisions, systems in the data plane establish sessions for secure information transfers. In the data plane, a subject, user, or service uses a system, such as a client-host PC, laptop, or smartphone, to make requests for a given resource. A resource is typically an enterprise app running on a server or cloud. Each request is mediated by a policy enforcement point. The enforcement point might be implemented as a software agent running on the client host that communicates with an app gateway. The policy enforcement point interfaces with the policy administrator to set up a secure data pathway if access is approved, or tear down a session if access is denied or revoked. The processes implementing the policy enforcement point are the only ones permitted to interface with the policy administrator. It is critical to establish a root of trust for these processes so that policy decisions cannot be tampered with. The data pathway established between the policy enforcement point and the resource is referred to as an implicit trust zone. For example, the outcome of a successful access request might be an IPsec tunnel established between a digitally signed agent process running on the client, a trusted web application gateway, and the resource server. Because the data is protected by IPsec transport encryption, no tampering by anyone with access to the underlying network infrastructure, switches, access points, routers, and firewalls is possible. The goal of Zero Trust design is to make this implicit trust zone as small as possible and as transient as possible. Trusted sessions might only be established for individual transactions. This granular or micro-segmented approach is in contrast with perimeter-based models, where trust is assumed once a user has authenticated and joined the network. In Zero Trust, place in the network is not a sufficient reason to trust a subject request. Similarly, even if a user is nominally authenticated, behavioral analytics might cause a request to be blocked or a session to be terminated. Separating the control plane and data plane is significant because it allows for a more flexible and scalable network architecture. The centralized control plane ensures consistency for access request handling across both the managed enterprise network and unmanaged internet or third-party networks, regardless of the devices being used or the user's location. This makes managing access control policies and monitoring network activity for suspicious behavior easier. Continuous monitoring via the independent control plane means that sessions can be terminated if anomalous behavior is detected. Zero Trust architecture examples.
Example. Description.
Google BeyondCorp. Google's BeyondCorp is a widely recognized example of a Zero Trust security architecture. BeyondCorp uses a system of multiple security layers, including identity verification, device verification, and access control policies, to secure Google's internal network. This has enabled Google to provide its employees with remote access to company resources while maintaining high security. Cisco Zero Trust Architecture. Cisco has developed a comprehensive Zero Trust security architecture incorporating network segmentation, access control policies, and threat detection and response capabilities. The architecture is designed to protect against a wide range of cyber threats, including insider threats and external attacks. Palo Alto Networks Prisma Access. Prisma Access is a cloud-delivered security service that uses a zero-trust architecture to secure network traffic. It provides secure access to cloud and internet resources while also preventing data exfiltration and other cyber threats. Rate your You should be able to summarize virtualization and cloud computing concepts and understand common cloud security concepts related to compute, storage, and network functions. Guidelines for implementing secure cloud solutions. Follow these guidelines for deploying or extending the use of cloud and virtualization infrastructure. Assess requirements for availability and confidentiality that will determine the appropriate cloud deployment model: public, hosted private, community, or hybrid. Identify a service provisioning model, software, platform, or infrastructure that best fits the application requirement, given available development resources and the degree of customization required. Consider whether the service or business needs could be better supported by advanced concepts. Microservices, serverless, and orchestration focus on workflow requirements rather than server administration. Benefits and common usage scenarios for software-defined networks. If using a CSP, create an SLA and security responsibility matrix to identify who will perform security-critical tasks. Ensure the reporting and monitoring of cloud security data is integrated with on-premises monitoring and incident response. Evaluate the security features of embedded devices and isolate them from other network devices. Implement zero trust architecture concepts to validate connections and devices instead of relying on inside and outside boundary concepts.